All right, day 25, section 7.4. We're going to talk about a topic today that might be a little bit more challenging than some of the previous ones. We're still working with ratios and proportions, and we're working with right triangles and um, different properties within triangles. But you want to take your time and make sure you have a good understanding of the corollaries and the theorems that we talk about today, and try and simplify it for yourself, and make sure you have an understanding of it, how it works for you. I'll show you some strategies, but make sure you figure out the best way that works for you. So the questions themselves and the definitions and the theorems aren't really as complicated as they come off. So let's get started. Theorem 7.3, the altitude to the hypotenuse. So think back what an altitude is. It goes from a vertex to the opposite side, and it's perpendicular to that opposite side. So the altitude to the hypotenuse of and this fill in the blanks a little messed up here, of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. Sorry, all my technology is lagging right now. The altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. So here, this is what we're talking about. The altitude to the hypotenuse. So here's the altitude that we're talking about. That altitude creates two small triangles inside that big right triangle. And actually, all three of them are right triangles. Now, you kind of have to flip them and rotate them, especially this one right here. So it is nice if you can kind of redraw these so you can see where their vertices are, so that you can see we have a big, a medium, and we have a small triangle, and they are all similar to each other. They share a lot of vertices, and they also share some legs. Some legs in one triangle are the hypotenuse in another triangle. So we really have to make sure we're able to separate these as we go through this lesson. All right, write the similarity statement. I'm sorry, what similarity statement can you write relating the three triangles in the diagram? So here's one triangle. Here's the middle triangle. And that's going to be W, so the right angle. This is Y, and this is Z. And then we have this small triangle. So this is W, this is X, take that back, this is Y, and this is X. See, I'm someone who really needs to separate these triangles. I'm not good at flipping things in my head and picturing all those rotations. So take your time, draw those out. So the similarity statement, I'm going to start with the big triangle, And I'm going to pick the 3. I'm going to go X, Y, Z. So X is at the end of the small leg. Y is the right angle. Z is at the end of the long leg. So that's similar to Y, W, Z, which is similar to X, W, Y. So we have the small triangle, we have a medium triangle, and we have the bigger triangle. So Q, P, R, S, P, R, S, Q, P. So Q, P, R, P, S, R, and QSP. All right, now when we draw this altitude in here, the location that it hits this hypotenuse breaks up this triangle in a very special way. And it breaks it up in what we call a geometric mean. And what that stands for is for any two positive numbers, and those numbers, let's just call them A and B right now, it is the positive number x. So the geometric mean is this number x such that if you take that number A and you divide it by x, it's going to equal the same thing as if you take that number x and divide it by b. And then we have a proportion. So what is the geometric mean? So 6 over x equals x over 15. Yes, this becomes quadratic. So x squared equals I jumped ahead a little bit too much. X squared equals 90. And then to solve for x, we take the square root. So x equals, now we don't want a decimal. We're going to practice a skill here that's an algebraic skill. We want to simplify the square root of 90. Now, yes, it can be written as a decimal, but it's an irrational number because 90 is not a perfect square. So we're going to take a break right here and review simplifying these. So this does seem to be a topic that can be confusing, a topic that can seem senseless, but it is just a number sense skill. Just if we were to go back and say 6 over 8, we can simplify that down by dividing the top and bottom by the same number and get 3 over 4. we can all admit that it's nice to know that 6/8 is the same as 3/4. And yeah, it's not a bad decimal to write. But if we did 6/9 and divide them both by 3, now we get 2/3, but that is not the best decimal to write. We would be forced to round that, and it's just not as accurate as keeping it in this form. Okay? I prefer to write my answers as fractions because it's the most accurate way to write that number, and we really don't write this repeating symbol too much once we're out of who knows what grade. So the same things applies. Now this is a rational number, okay? That's it repeats. The top one terminates. So these are rational numbers. Irrational numbers do neither of that. They go on forever like pi. No rhyme, no reason. There's no rational reason for what pattern evolves. Actually, no pattern evolves. So if we take something like the square root of 4, we know that that equals 2 because we can change 4 into 2 times 2. Now, I just changed the way that looked. I did not change the value of that. And really the same thing goes up here. If we really want to know how did you know or how did I know I could divide by 3, well, that's because I know I could rewrite this as 2 times 3 over 3 times 3. I changed the way it looked. I didn't change the value of it. So now I can see there's a 3 in the top and bottom. Therefore, we can take a 3 out of both the top and bottom. So it's this idea of taking a number and cracking it open to see what's inside. Now, the more formal way to say it is let's factor it. Let's see the factors that are inside of it. So factoring here is going to be useful for us. Same thing down here. I'm going to factor the 4 so I can see the 2 numbers. That's how you know that 4 is a perfect square, because inside of it, you have factors that are duplicated, that are paired up, that are doubles, that are twins, however you want to say it. If it was a perfect cube, we would want 3 instances of that. Like if this was 8, we can split it into 2, 2, and 2. We have a triplet. That means it's a perfect cube. So we like these. We like perfect squares, like 9. It's 3 and 3. So we can simplify this. Anytime you have a pair of numbers, it all just goes down to what that number is. So you have a pair of 2s, this whole thing just turns into one nice 2. You have a pair of 3s being square rooted, that all turns into just one nice 3. Now most of us can just go from the square root of 9, 3. Square root of 4, 2. Your goal is to be able to find these perfect squares inside of numbers that are not perfect squares. Just like up here, we are able to find these similar factors inside numbers that are not the same. So, is this a perfect square? No, because you don't have a number times itself that equals 8. So your goal is to change it. Instead of 8, let's find 2 factors that multiply to give us 8. We can do 1 and 8, or you can do 2 and 4. There's really no wrong answer. 1 and 8 is not going to get you anywhere, though. You want to try to expose the perfect squares. And we know 4 is a perfect square. I like to put the perfect square first. It makes it a little bit easier here coming up. 4 times 2. And then we have a property that says the square root of 2 factors can split up into 2 separate square roots. So what I did right here is the same thing as if I did this. Now, I know a lot of you do not do this step when you simplify a fraction. So when you're ready, you guys can skip these steps and just say the square root of 4 is just 2. And that square root of 2 is left there. So we say that's 2 radical 2. Let's try another one. The square root of 45. Now you might say 3 times 15, but 3 and 15, neither of them are perfect squares. So what are other two factors where one of them is a perfect square? Hopefully you're saying 9 times 5 out loud. We can separate that. You don't have to separate them if you can go straight to the final answer. I just know in the past, sometimes it confuses kids why this stays the same and this disappears. It's because when you separate them, the square root of 9 is 3, and the square root of 5 can't do anything. Now, what if somebody did do 3 times 15? Well, then that person would have to keep going and keep breaking apart that number. Now, remember what we said over here. If you have a pair of numbers, they don't have to be next to each other. Here's a 3 and here's a 3. Associative property says we can flip those around. Or technically the commutative property, depending on which way you're thinking of it. And now there's 9 and 5. So there's this little number theory and a little bit of number sense in there for you. Now, I'm not saying that you would have went through all of these steps. Maybe you like this route. That's fine. There is a short method and there is a longer method. Let's do one coming up here. $72. Now, 9 might be jumping out in your head. 9 times 8. And you would be right. But you did not simplify it all the way. Because what is still inside that 8? Another 4. What that means is we did not find the biggest perfect square that is inside of 72. And we kind of know now what the biggest one was, because if I take this back and go backwards, this 6 came from the square root of what? 36. So I should have done 36 times 2 from the beginning. The bigger the perfect square that you can take out from the beginning, the faster the process will be. So we could have done this in 3 steps. Who knows? If you skip this step, you might be able to do it in 1 step. So here's what you want to aim for. If you have a number, is it a perfect square right away? Chances are no. If it's not, the longest way is to break it up into your 2 favorite factors and then go searching for pairs of numbers. Or start dividing out or exposing the perfect squares inside those numbers. The bigger the perfect square, the shorter the process. All right, so let's go back to 90. Ninety is 9 times 10. So maybe you skip that step. Maybe you start going straight to that step. That's perfectly fine. So x equals 3 times the square root of 10. Now, we just did a lot there. Remember, that was just a side break when we talked about geometric mean. Remember, geometric mean is this proportion where we have this geometric mean showing up in the denominator here, numerator here, and that causes this to be quadratic. And really, there's another way to write this geometric mean. We can go here and then just write it as such. We can write it as x squared equals I'm going to use the same colors. X squared equals AB. Or you can think of it as x equals, because we want to know what the geometric mean is. So this is kind of a favorite right here. X equals the square root of AB. So let's do that for this bottom one here. X equals the square root of AB. There, we just saved ourselves some work. And notice what else happens. Since we don't multiply these together, we already have them separated, and 4 is a perfect square. So let's take advantage of that and say the square root of 4 times the square root of 18. I know some people don't like to simplify anything to the very end, so I'll show you what that would look like. Notice I went straight from 18 and I split it up, the 18, and I split up the square root all in the same step. So basically I went from here, skipped that step, and went to here. Now don't start bringing things back together yet. This is 2 times 3 times the square root of 2. So 6 times the square root of 2. Don't try and memorize them. Like that one would have been the square root of 72. Don't try and memorize what the square root of 72 simplifies down to, because there's questions that will force you to be confronted with something you don't know possibly. All right. Here's some illustrations here that show you how geometric mean applies to this triangle with this altitude. So if you take the triangles that are similar, the short leg is actually, the short leg in this smaller triangle and the short leg in this medium triangle. Now this is actually the long leg of the small triangle. That's how this segment will show up in both ratios, but in different locations. For this triangle, it's going to be up top. For this triangle, it's going to be down below with the short. And there's that XX idea for geometric mean. So SP, so this altitude that we've been talking about is actually the geometric mean, meaning its length. Corollary 1 to 7.3. The length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So looking at this figure, we have AD over CD equals CD over DB. So AD over CD equals CD over DB. That's an A. DB. This proportion is going to be the one that shows up with a lot of algebraic work. Now there's a counterpart to this one as well. We're going to do it here in a little bit. And here's the way I like to think of these. There's 4 parts of a proportion. Okay, these ones will always be the same. So I like to call this one the heartbeat proportion. So it's basically saying AD, and then it goes up, back down, and over. So kind of like a heartbeat. Beep, just like that. So AD over CD, CD over DB, the heartbeat. Meaning, it doesn't matter what side you start from. So 2 over 4, 4 over 8. I'll do that again. 2 over 4, 4 over 8. So that's the heartbeat. 2 over 4, 4 over 8. So what it's doing is basically this altitude breaks up this hypotenuse based on a geometric mean. So this segment of the hypotenuse over the altitude, and then this altitude over this segment of the hypotenuse. That's what's happening here. All right, corollary 2. The altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean. So now it's not the altitude that's the geometric mean, it's the length of each leg is the geometric mean. The altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg is the geometric mean. Of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. Now that's a lot. And remember what I said earlier, even before we started, these definitions, these theorems, and these corollaries, they're worded where you have to read them many times and compare them to the visual to understand what's happening. So what's happening here is we have segment AB, which is a hypotenuse, over segment AC, which is a leg, but it's also a hypotenuse of the small triangle, equals AC over AD. So you have the hypotenuse over its leg. So AB, oops. So the big hypotenuse over the big triangle's leg, but this big triangle's leg is also the hypotenuse of the small triangle. So now it's going to be represented up top because AB over here is a hypotenuse. So up top is a hypotenuse, and AC is also a hypotenuse. And its corresponding leg that it goes with is AD. And yes, you can do that on the other side as well. So you could say AB over CB, and then CB over DB. The reason why those show up twice is because right here, AC is a small leg, adjacent leg, I should say. Here, AC is a hypotenuse. Here, CB is an adjacent leg. Here, CB is a hypotenuse. And the way that I like to remember this, remember the other one we had the heartbeat. This one we have the boomerang. So for the boomerang, we go here, and then we come back around. I'll do that again. So somebody's standing right here. They're going to throw the boomerang. It goes around the corner, and then it comes all the way back around. Let's just say this person did not catch it. We could go this way, and it comes all the way back around. Now, this person throwing the boomerang has to miss it because we have to come all the way from B all the way to A. So here's what I mean by that down here. 1 over 2, I'll switch colors, 2 over 4. So 1 over 2, 2 over 4. Notice 2 is in 2 different colors because it's green on the way up and then it's red on the way back. Because it's a hypotenuse here, it's a leg up here. Notice how my proportion is different than theirs because it's just flipped. 4 over 2, 2 over 1, 1 over 2, 2 over 4. It's the same idea. Okay. So what are the values for x? So you have to understand, is this a heartbeat problem or is this a boomerang problem? That's the way I like to think of it. Not very formal, but it works. Notice x is out here for boomerang, y is inside for the heartbeat. Okay, I'm going to go after the y first. So heartbeat, right? Boop, just like that. So 4 over y, y over 12. So that means y equals the square root of 48. I went straight to that. Let me slow that down. Y squared equals 48. So y equals the square root of 48. What's inside 48 that's a perfect square? 16. The square root of 16 is 4. So y equals the square root, or 4 times the square root of 3. All right, let's go after x. X is over here, so x is going to be compared with this 4. If x was over here, we'd be comparing this to the 12. So we're going to do the boomerang motion. So person's throwing the boomerang at the bottom here at the altitude. So 4 over x, x over 16. Well, that one should make us happy because 64 is a perfect square, so x equals 8. All right, this one's a little bit easier to look at because it's not rotated like the other one. So 4 over y, y over 5. 4 over y equals y over 5. So y equals the square root of 20. And to be honest, like I said earlier, going 4 times 5 to 20, really, there's more benefit to writing it like a times b because we need to break 20 up already, and 4 is a perfect square, so let's go for y here. I'm sorry, for x. 4 over x, x over 9. 4 over x, x over 9, x equals the square root of 36, which is 6. All right, you're preparing for a robotics competition using the setup shown here. Points A, B, and C are located so that AB equals 20. They wrote that in there for us. AB is perpendicular to BC. Point D is located on AC so that BD is perpendicular to AC. And DC equals 9. You program the robot to move from A to D and to pick up the plastic bottle at D. How far does the robot travel from A to D? Sure, we didn't skip a problem. I feel like I skipped one. Okay. All right, so notice where x is. We have 20, which is our hypotenuse. This altitude has nothing to do with this problem. So it's not going to be a heartbeat, it's going to be a boomerang. So x over 20, 20 over equals 20 over x plus 9. Notice how I had to add these together here. So 400 equals x squared plus 9x. This is quadratic. We're going to subtract 400 from both sides. So that's x squared plus 9x minus 400 equals 0. So we need to factor this. And this is going to be x plus 25, x minus 16. And because positive 25 plus negative 16 is positive 9, and then 25 times negative 16 is negative 400. So x equals negative 25. X equals 16. X cannot be a negative number, so x has to be positive 16. So there is some good factoring review for you right there. Let me explain what happened down here. Hopefully you guys recall this. It's telling us that these two things are being multiplied to equal 0. If that's the case, then one of these things has to be 0. So I set this equal to 0, and I set this equal to 0, and I solved each one. X minus 25 is a valid answer algebraically, but in context of this problem, it just can't work out. From point D, the robot must turn right and move. All right, let's try this next one. From point D, the robot must turn right and move to point B to put the bottle in the recycling bin. How far does the robot travel from D to B? So this is what we're trying to figure out. We know this is now 16. So x is in the middle now. That's a heartbeat problem. So 9 over x, x over 16. So that is x equals the square root of 9 times 16. Hey, look, 9 and 16 are both perfect squares. So that means this is going to be x equals 3 times 4, so x equals 12. All right, take your time, rewatch some of that, pause it, take a look at the work. Make sure you guys are asking me questions. Tune into the office hours. Make sure you check out this homework down below. We have one more section in this unit before we review and then take the Unit 7 test.